Hello everyone, it's time to grab your banana smoothie because we're talking about threads. This is part 2 of a short series explaining Neuralink's 2019 white paper titled An Integrated Brain-Machine Interface Platform with Thousands of Channels by Elon Musk and Neuralink. The previous video explained the paper's introduction, the scope of Neuralink's mission, and the technical components required to fulfill it, namely electrode threads that stay in the brain without causing any trouble, a surgical robot to insert them, electronics hardware, and software to interpret the signal. The next section of the paper is about the design of the electrode threads themselves. As with the first video, my goal is to make the white paper understandable to people who are not experts. To cover everything, I had to break this single section into 2 different videos. This video is about the design of the threads, and the next one is a deep dive into the manufacturing techniques that are used to build them. Let's examine the thread architecture within the context of the goal that Neuralink is trying to achieve. Remember, the brain is teeming with electrical activity, and the patterns of that electrical activity contain information. Neuralink is trying to detect these patterns in high fidelity. To do this, the link contains thousands of tiny wires that can propagate electrical changes from a minuscule region of brain tissue to a computer embedded in the skull. We'll start with an excerpt from the second section of the paper. Again, feel free to skip ahead if you just want to go to my explanation. We have developed a custom process to fabricate minimally displacive neural probes that employ a variety of biocompatible thin film materials. The main substrate and dielectric used in the probes is polyamide, which encapsulates a gold thin film trace. Each thin film array is composed of a thread area that features electronic contacts and traces, and a sensor area where the thin film interfaces with custom chips that enable signal amplification and acquisition. A wafer-level microfabrication process enables high-throughput manufacturing of these devices. 10 thin-film devices are patterned on a wafer, each with 3,072 electrode contacts. In this section, the term array refers to the whole set of probes on a single Neuralink device. The probes are tiny groups of wires. Each wire within that group is made of a conductive trace of gold encased within a high-performance biocompatible plastic insulator. At the end of each gold wire, there's a bit of the gold which is not insulated. This region functions as an electrode, a part of the wire that is capable of direct electrical interactions with the region of brain tissue it is embedded in. At this point of brain electrode contact, electrical current can be exchanged between the probe and the tissue environment. Changes in current propagate from the electrode interface along the tiny wire to a sensor region on the main Neuralink hardware stack. Here's a picture from the Neuralink launch event. One of these early thread designs is on the right and a human hair is on the left. The red arrows point to one of the bulbous terminal electrode regions of one of the thread's tiny wires. Changes in the electrical potential at this exposed tip result in changes in the current conducted along the thin gold wire all the way to where that gold trace connects to the sensor region of the Neuralink. If you look closely, you can see the tiny trace gold wire that is continuous with each electrode bulb. Each of these gold wires is its own electrical channel, an isolated physical line, and which represents a distinct flow of information about how that particular microenvironment in the brain is behaving electrically. Notice that this thread is thicker at the bottom of the image and thinner at the top. That's because each of the tiny gold wires is separated from the others by an electrically insulating material so as to prevent channel crosstalk. More gold wires means a thicker thread. And as you go from the bottom to the top, one gold wire after another terminates into an electrode. So fewer insulated wires need to run to the more distal points on the thread, meaning that the thread size can taper as it gets closer to the distal end. Another thing to notice from this image is the little loop at the terminal end. That's the part of the thread that attaches the guide needle which the surgical robot uses to insert the thread into the brain. Here are some of the thread designs shared from the Neuralink launch event. Notice the differences in shape and channel count, which you can infer from the number of electrode regions on each thread. Some of the threads use the electrode ends as barbs, which could help prevent the thread from working its way back up out of the tissue once it's placed in the brain. The paper describes the threads as minimally displacive, biocompatible, and made from thin film materials. Displacive refers to spatial displacement of the brain tissue caused by the electrode implant crowding out the brain. Remember, the skull is fixed in size, and the adult brain is full of millions of mature neuronal circuits that require spatial stability to function normally. To be minimally displacive, the threads are manufactured to be as small as they possibly can, so that their presence throughout the brain doesn't compress and disrupt the tissue any more than is absolutely necessary for the functional goal of the implant. The smaller the threads, the more of them you can fit into the brain with fewer negative effects of crowding out the tissue. Biocompatible refers to the lack of toxicity and immunogenicity. In other words, the ability of the implanted hardware to not kill cells and destroy tissue while also not generating an immune response. One immune response that impacts the function of the electrodes is the foreign body reaction, where a foreign object is surrounded by immune cells, notably macrophages that fuse together, and fibroblasts, which create a barrier of cells and scar tissue and isolate the foreign object from the rest of the tissue. This rejects the implant and confounds the ability of the electrode to detect neuronal action potentials as it would in normal brain tissue. The major goal of biocompatibility is for the implant to be either immunologically cloaked or immunologically benign, such that the physical shape and electrostatic signature of the implants are undetectable to the immune system, or at least if they are detectable, they don't activate it. To achieve this, the implant should be invisible to pattern recognition receptors, antibodies, and other free-floating proteins whose job it is to adhere to and mark pathogens and debris for destruction and rejection. This is achieved primarily by the electrochemical and mechanical properties of the materials that the probes are made of, but you can go beyond these materials by adding biological coatings to minimize inflammation and scarring around the probes, which further extend the duration of time in which the electrodes can detect high-quality electrical signal. DJ mentions that the team is experimenting with these kinds of biological coatings.
Things that we are actually actively working on is having some sort of biological coating to either reduce inflammation or make them slippery. So, you mentioned, you heard from the presentation that one of the challenges that we have is removing the threads from these neomembrane tissue that are formed after implantation. So there are programs like that where we're really looking at kind of incorporating some of the learnings from biology and these coatings into our threads so that we can hopefully reduce inflammation as well as make it easier to extract.
The paper mentions that the main substrate and dielectric used in the probes is polyamide, which encapsulates a gold thin film trace. Polyamide is a high-performance plastic and functions as a dielectric. A dielectric is functionally similar to an insulator in that it's non-conductive, but the functional difference between an insulator and a dielectric is that the dielectric is capable of becoming electrically polarized. So when an electrical field is applied, the atoms in a dielectric reorient themselves to result in an accumulation of positive and negative charges within the material without allowing a significant current flow through it. When a current runs through the gold trace of one of the Neuralink threads, the surrounding dielectric polyamide itself will polarize, meaning that the positive and negative charges within that material will separate and create their own electric field. This polarization creates a counteracting electric field that can partially shield the external electric fields from interacting with the field at the core of the cable as current runs through it. So compared to a passive insulator like rubber, a dielectric insulator actually actively produces an electric field to help insulate the current and becomes even better as an insulator the more current runs through the gold line. This is a subtle difference, but you can pretty much just think of it as an insulator on a wire and you have the basic design correct. It insulates the different gold channels electrically from each other so that there isn't any crosstalk. This is what an amide looks like. It's a nitrogen connected to two carbons, each of which is double bonded to an oxygen. As you might guess, a polyamide is a molecule made from combining multiple amides. There are tons of chemicals that fall under the umbrella term of a polyamide. Technically, anything with multiple of these groups is a polyamide, but the ones that are most common in biological implants and flexible electronics are aromatic polyamides, which are composed of the amides as well as aromatic rings. So I assume that's what Neuralink used for their prototype. These chemicals are useful because the chemical bonds of polyamides are extremely stable, which makes them resistant to corrosion, oxidation, and other types of chemical degradation. They're also thermally stable, meaning they preserve their material properties when exposed to heat. Polyamides are non-conductive, chemically inert, electrically insulating, and importantly, can be used in microfabrication techniques. Polyamides are also famously biocompatible. They're already used in medical devices today. These properties are crucial for long-term residency in the brain, as anything that lives in the brain has to be resistant to decay when it's exposed to free radicals, ions, and other reactive elements in the tissue environment. Okay, so polyamides are the main insulator and form most of the total material of one of the threads, but what about the conductive element, gold? Gold was chosen as the main conductive metal for the threads, even though silver is more conductive, cheaper, and has a similar material hardness, because gold is less prone to corrosion when it's exposed to chemicals that are relatively common in biological tissue. Neuralink probably uses gold as the conductor instead of silver due to the superior chemical stability of gold, and its deep history of use in microfabrication of integrated circuits, microelectronics, as well as biomedical devices. Now we've got an idea of what the threads look like, how they function, and what they're made out of. The next part of the paper zooms out a little more to consider how a group of threads works on the whole Neuralink. Each array has 48 or 96 threads, each of which contain 32 independent electrodes. Integrated chips are bonded to the contacts on the sensor area of the thin films using a flip chip bonding process. One goal of this approach is to maintain a small thread cross-sectional area to minimize tissue displacement in the brain. To achieve this while keeping channel count high, stepper lithography and other microfabrication techniques are used to form the metal film at submicron resolution. The term array in this section refers to all of the threads of a whole Neuralink device. This prototype Neuralink has 96 different threads, and each thread has 32 electrodes for a total of 3,072 channels. This is a screenshot I grabbed from a Neuralink YouTube video uploaded in January of 2021 called Working on the Neuralink Robot. The design of this Neuralink is different, but this picture makes it easier to see how the threads are spatially organized when they go back to the main board. Notice how each thread appears to run to multiple terminal points on the chip. That's because each thread is actually a bundle of distinct electrical lines, distinct wires, and each of these wires must have its own point of contact on the board so that the electrical signal from that line is kept separate as a separate channel until it's converted into digital information. Because Neuralink wants to keep the threads tiny, they're built using microfabrication techniques. Microfabrication is the engineering art of accurately building with materials at a level of precision measured in micrometers or submicrometers. Think of all the internals of your computer or your smartphone. All those integrated circuits and multi-circuit boards are built using microfabrication techniques. Without microfabrication techniques, a computer as powerful as your laptop would take up the size of a small gymnasium. There are many kinds of techniques that fit into this umbrella category, but the ones specifically mentioned here are photolithography and flip chip bonding. In the next video, we'll go over these fabrication techniques as well as the others that were likely used to build the prototype threads.